Hey everybody, it's Mr. Carr again. Today we're going to be looking at 1.6, function operations and composition functions. Okay, so what that means. The first part is, so some of the things you've already done, you evaluate functions back in section 1, as well as other classes. We're going to perform certain operations with our functions, as well as doing what's called compositions. So let's start with focusing on the operations. Here we have sum, difference, product, and quotient. Bottom line is, if we want to say the sum of two functions, we simply add the two functions together. The product of two functions, f times g of x, we take both functions and just multiply them together, okay? It's really just following those along. If we are subtracting f minus g of x, make sure you're doing it in the correct order, but f of x minus g of x. And the quotient, if I have f over g of x, that's the same as taking the function f of x divided by g of x, but we gotta be careful because the g of x function cannot be 0. So that's where we got to be careful so we don't divide by 0 in that case. Okay. So find each of these for the two functions f of x equals x squared plus x and g of x equals x minus 3. State the domain of each new function. So we'll start with this one first. We got f plus g of x. So we're going to do f of x plus g of x, which is going to look like x squared plus x minus 3. So f of x plus g of x. We just have these two combined like terms. We got x squared plus 2x minus 3. Now, when we state the domain of this, we just got to look for, are there any restrictions? Okay, so from the originally, there is no restrictions on that because it's just dealing with a quadratic and a linear. So when we combine them, our domain is just going to be all real numbers. In terms of interval notation, it looks like this, negative infinity to infinity. Okay, so we'll do f of x minus g of x now. And that's going to be x squared plus x. When you do your subtraction, I'm going to highly suggest you put it inside parentheses for your function. Okay, because you got to be careful with how you do your subtraction. So I got x squared plus x minus x and then plus 3. Okay, so now if we combine these two together, they're going to cancel each other out. So my new function here is just x squared plus 3. Same thing. Are there any restrictions on domain? Nope. So that means it's just negative infinity to infinity. All right, so f times g of x. So we're going to multiply our two functions together. Okay, so that is going to be, and since I'm multiplying, I'm going to leave it like this, x squared plus x multiplied by x minus 3, which means we need to distribute. So the multiplication of these two, if I distribute the x squared, that's going to be x to the third minus 3x squared. Then I got x here is going to distribute, so I got plus x squared. Whoops. Sorry, I forgot. Minus 3x squared. And then plus x squared minus 3x. Combine my like terms so that the multiplication of these two is going to come out as a negative 2x squared minus 3x. And once again, the domain, this is just a cubic function. The domain is going to be all real numbers. There is no restrictions on a cubic function. For my last one, we're going to have f of x over g of x. Okay, pretty sure. Yep. And that's going to end up being x squared plus x over x minus 3. Now, remember with this one, because our domain is like our domain is going to be restricted because we cannot divide by 0. So we got to ask ourselves what value of x would make this a 0 denominator. So I could say x minus 3 cannot equal 0. So x cannot be 3. So as long as this function, so this function exists, the f of x over g of x, as long as for our domain, we say it's negative infinity to 3, union 3 to infinity. So it's all real numbers except for a positive 3. Okay, so that's our first operations. The next thing we're talking about is what's called the composition of functions. A composition of a function, so we look at this one, we read it as f of g of x. Basically, it looks like this. The domain of f of g is all the x values that would be part of the domain of g that also map into the function of f. Okay, so basically we're taking the entire g of x function and plugging it inside the f of x function. So the domain of a composite function So we take the domain of the inside function. That's the function that you're going to substitute in. And it's going to go to the domain of the composite function. They have to line up that way. All right. So if there's ever any restrictions on the original function, on the inside function, those same restrictions apply to the composite function. So remember, when it's written this way, if it's f and then g, g is going to go inside of f. If I did it the other way, where I did g o f of x, then that is going to be swapping that. It'll be the f of x function inside. Whoops. There we go. So f of x will actually go inside. So the order of the letters matter in this case. So let's take a look at this one. We're going to compose these two functions. So in this case, we want we want f of x going inside of g of x. So it's going to look roughly like this. G of f of x now is going to equal to, where am I at? F of x here. This whole function is going to go into that spot right there. So here's how I like to do it. I'm going to set parentheses and then +3. I'm writing that g of x function, but instead of an input of x, I'm going to leave it as a blank, open blank. 2x squared minus 1 is what's going to go in there. So I can put that 2x squared minus 1 there. Last step is just to simplify where I can. So there's nothing else, no other operations to do besides -1 plus 3. So to simplify this, that'll be g of f of x equal to 2x squared plus 2. And that's it. No other follow-up questions on this one. So let's move on to, is it our last? Nope, not quite. Move on to the next one. Find f of g of x, then find the domain, then find f of g of -2. So in this case, g of x is going to go inside f of x. So it'll be f of g of x. So in this case, for my f of x, I'm going to just write 1 over, I guess, blank. But I'll leave it like that, I guess. G of x is going to be my input, so it'll be the square root of x squared minus 1. Okay, so now my function, my composite function, it looks like this here. My restriction on this is 2 things. Don't forget, we cannot have a 0 in our denominator. But because of the square root sign, we can't have a negative number down there either. So the idea is this. To be both, it's got to be greater than 0 inside that radical. So x squared minus 1 needs to be greater than 0 for the domain. So if I solve that, x squared has to be greater than 1 when I add it over. And then when I square root this, that means x has to be greater than a plus or minus 1. Okay. So, give me 1 second here. Okay, sorry about that. I'm going to modify my solving here because dealing with quadratics with our square root like that makes it a little bit trickier. So here's what I'm going to do. I'm going to solve this. So x squared is equal to 1, and then I square root, so I get plus or minus 1. This is going to create critical values. So I'm going to model this real quick on a number line. So I'm just focusing on this function right now because that's going to be our real test here. I've got -1 and a +1. I'll put 0 in the middle, and then -2, and then a +2. So again, the key here is this, when I plug it in there, has to come out as greater than 0. Okay, so it can't equal 0, so it's got to be greater than 0. So we know that if I plug in -1 and 1, that's actually going to create a 0. -1 squared is 1, -1 is 0, square root of that is 0. So these are going to be kind of like open holes here for -1 and a +1. So let's take a look at what happens with the rest of these. Let's say I plug in a -2. So I plug in a -2, I'm going to get -2 squared is +4. +4 minus 1 is 3. That's greater than 0. That's what I want. So this is good. So this works here. Okay. If I plug in a 0, 0 squared is 0, minus 1 is -1. That's not greater than 0. I want this x squared minus 1 to be greater than 0. That's the goal. So this is actually no good. And then if I do the same thing on the other side, so sorry, I should do this. Everything to the left here of -1 should work. If I do 2, 2 squared is 4, 4 minus 1 is 3. So everything to the right here. So my domain has 2 intervals. It is everything that's less than -1. So it's going to be a negative infinity to a -1, union 1 to infinity. These are the 2 intervals that work for this function. Okay. Now, finding f of g of 2, sorry, f of g of -2. it's going to look like this. F of g of -2 equal to 1 over the square root of -2 squared minus 1 now. Okay, so f of g of -2 is equal to 1 over the square root of 4 minus 1, which is equal to 1 over the square root of 3. Now, lots of times we'd like to rationalize the denominator, so let's go ahead and get that back in the habit of that. So we're going to multiply by the square root of √3 over √3. So my function is going to be, or my output is going to be the square root of 3 over 3. There. So we found f of g of -2. We have our domain. This problem is finished there. All right, let's look at, I believe this is the last one. Okay, decompose a composite function. We want to find two functions f and g such that h of x is equal to f of g of x. So h of x is going to be this right here, 1 over x plus 2 squared. Neither function may be the identity function f of x equals x. So I don't want to use that. There's probably a couple ways we can do this. I'm going to look at what I think the easiest thing to do. First thing I notice is this is a reciprocal function. And that is going to be, this looks like this is inside that one. So if that means my f of x function, I'm going to make that 1 over x. Okay. So now the question is, how do I make this denominator look like this? That's what the g of x function needs to be. Well, if I'm replacing that x input for f of x with the g of x function, it's just going to be the x plus 2 squared. Okay, so that if I take this and put it inside that, it will look like this. Okay, good idea to go ahead and double check that, just be on the safe side. But if I do that, it's going to be 1 over x plus 2 squared when I plug it back in. All right. And that is it for 1/6. So with remember our function operations, we can add functions, subtract them, multiply them, or divide them. Just make sure when you divide functions, you're considering the fact that you cannot have 0 in the denominator. The other thing we do is composition functions, which is a basic idea is one function goes inside of the other function. Creates a brand new function, so we just got to analyze our domain and look at potential restrictions there. But basically, the domain of the inside function is going to be inside a part of the composite function unless there's other restrictions that come up. All right. And that is it for today. Take care, everybody. See you next time.